Now, in this lecture, we find out the area of a circle. In the drawing, we have a circle that is inscribed by trapezoid ABCD. We also know that this is line segment AM that is equal to units in its length. This is line segment MB that is equal to B units in its length. Again, our mission is to find out the area of this circle that is described by trapezoid ABCD. So, first of all, we will implement here rule 2. So, I'll put click on rule 2. According to rule 2, the lengths of two tangents from common center points to a circle are equal. So, in the drawing, we have a circle, and this is the common center point, point P. From this common center point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. Why? Because in our drawing, if we focus on this common center point, point A, from this common center point, point A, we have two tangents to this circle, tangent AM, and we have also this tangent. So we define the point of tendency, tangent AD with this circle. This point is point P, and we define the point of tendency of this tangent BC with this circle. This point is point Q. So at the common center point, point A, we have two tangents to this circle, tangent AM and tangent AP. And according to rule 2, they are equal to each other. That is to say, AM equals to AP. But AM equals to A, therefore AP must be also equal to A according to rule 2. Likewise, we'll focus on this common center point, point B. From this common center point, point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to B, therefore BQ must be also equal to B units in its length. So this is tangent BQ is equal to B units in its length according to rule 2. In the next step, we define the center of this circle. This point is point O, and we join points O and P together by a straight line. What is the definition of line segment OP? Line segment OP starts from point O, that is the center of this circle, and then at point P, that is the point of the circle itself. So this is exactly the definition of a radius. Therefore, OP is the radius of this circle, so we define the radius of this circle as x. So OP equals to x is the radius of the circle, according to our definition. And here, because of the fact that the radius of P that is equal to x, the radius of P is drawn to point P, that is the point of tendency of tangent AD with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and Q together by a straight line. OQ is of course the radius of this circle. It is equal to x, and because of the fact that the radius OQ that is equal to x, the radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO according to rule 1. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we do a construction That is to say, from this point A, we will draw perpendicular on BC. Again, from point A, this point A, we will draw perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point A in BC. This point is point N. ABCD is a trapezoid. A trapezoid is a quadrilateral with one pair of parallel sides. So in trapezoid ABCD, side AD is parallel to side BC. So we know that AD is parallel to BC, and those two angles, they are located between the two parallel lines AD and BC. Those two angles are defined as one-sided interangles, and according to Rule 17, the sum of two one-sided interangles that are located between two parallel lines is equal to 180 degrees. So I'll repeat quickly on Rule 17. According to Rule 17, the sum of one-sided interangles that are located between two parallel lines is equal to 180 degrees. So in the drawing, we have line A that is parallel to line B. The red line C intersects with those two parallel lines A and B and those 2 points. And also here, those two angles, alpha and beta. Those two angles, alpha and beta, they are defined as one-sided interangles. They are one-sided angles because both of them are located on the left side, on the same side that is the left side of the red line C. And they are interangles because of the fact that both those two angles are located between the parallel lines A and B. So in total, those two angles, they are defined as one-sided interangles. And according to this rule, Rule 17, the sum of two one-sided interangles is equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So can actually implement Rule 17 in our drawing. Why? Because in our drawing, as I already mentioned before, those two angles are defined as one-sided interangles, and they are located between the parallel lines AD and BC. I repeat again that AD is parallel to BC because of the fact that ABCD is a trapezoid, and a trapezoid is a quadrilateral with one pair of parallel sides. So this trapezoid ABCD, AD is parallel to BC. So those two angles are defined as one-sided interangles, and they are located between the parallel lines AD and BC. Therefore, the sum of those two angles is equal to 180 degrees. This is a right angle. It is equal to 90 degrees in its size. So 90 degrees plus this missing angle, in total the sum of those two angles must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. According to Rule 17, of course. In the next step, we will do another construction. That is to say, from this point O, that is the center of this circle, we will draw perpendicular on A again. From point O, we will draw perpendicular on AL. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point. We will define the touching point of the perpendicular from point O and again this point is point T. By doing this construction, we created the small quadrilateral ATOP. This is the small quadrilateral ATOP. Inside this small quadrilateral ATOP, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this fourth missing angle must be equal to 90 degrees in its size. Likewise, we have the small quadrilateral TOQN. Inside this quadrilateral TOQN, we have 1, 2, 3 right angles. Again, the sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So if we found out that the big angle POQ, this is the big angle POQ equals to 90 degrees plus 90 degrees. 90 degrees plus 90 degrees is equal to 180 degrees. So the big angle POQ equals to 90 degrees in its size, and therefore POQ is a straight line. Again, POQ is a straight line because of the fact that angle POQ equals to 180 degrees in its size. So I write it down. Now we found out that because of the fact that angle POQ equals to 180 degrees in its size, therefore line segment POQ must be a straight line. Okay, POQ is a straight line. So if POQ is a straight line, it means that PQ is also a straight line. PQ is a straight line. So actually, this shape ANQP, consists of 1, 2, 3, 4 sides. So write it down. Shape ANQP consists four sides and therefore APQN is a quadrilateral. Okay, shape ANQP is a quadrilateral okay. Any shape that consists of four sides must be a quadrilateral. So APQN is a quadrilateral. But APQN is a quadrilateral with 4 right angles. APQL is a quadrilateral with 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to this quadrilateral APQN as a rectangle because it has 4 right angles. No, the big quadrilateral APQN is a quadrilateral according to rule 5. It is a rectangle according to rule 5. Again, any quadrilateral that has 4 right angles must be at least right angle plus the square, so we need to quadrilateral APQN is right angle because it has 4 right angles. So for A quadrilateral APQN is right angle according to rule 5. But we also know that the opposite sides of a right angle are equal to each other. So in right angle APQN, side AP must be equal to the opposite side NQ, but AP is A, therefore NQ must be also equal to A units in its length. So what is the length of this line segment BN? From the drawing it is very easy to see that BN equals to BQ minus NQ. Again, BQ minus NQ equals to BN. So I write it down. BN equals to BQ minus NQ. So BN in total equals to BQ is B according to rule 2, minus NQ is A. So total BN equals to B minus A units in its length. This is 97 BN, that is equals to B minus A units in its length. So in rectangle APQN, the opposite side PQ is equal, the side PQ must be equal to the opposite side AN. But PQ equals to X plus X. PQ is a straight line, and in total PQ equals to X plus X, that is 2X. Therefore, the opposite side AN must be also equal to 2X units in its length. So here we should find out that AN equals to 2X units in its length. Side AB here in total it is equal to A plus B. So it is known AB equals to A plus B. So in the next step I'll copy the right triangle ABN, and in the present we will implement the Pythagoras theorem on this right triangle ABN. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a relation of Pythagoras theorem. Okay, this is the right triangle A and B that I go with from the original drawing. In this right triangle A and B, the hypotenuse AB equals to B plus A units in its length, AN equals to 2X units. This is side BN that is equal to B minus A units in its length. According to the Pythagoras theorem, in this right triangle ABN, the square of the hypotenuse that is AB square is equal to AN square plus BN square. So I write it down. AB square, that is the square of the hypotenuse, is equal equal to an squared plus bn squared. The hypotenuse AB is equal to b plus a units in itself, therefore ab squared is b plus a squared, and it is equal to an squared. An is 2x, therefore an squared is 2x squared, that is 4x squared, plus bn squared. Bn is b minus a, therefore bn squared is b minus a squared. So in total, we found out that according to the Pythagoras theorem, b plus a squared equals to 4x squared plus b minus a squared. We open the brackets on both sides of this equation, and we get that b plus a squared equals to b squared plus a squared plus 2 times a times b, and it is equal to 4 times x squared plus b minus a squared. B minus a squared equals to b squared plus a squared minus 2 times a times b. So here we have b squared on both sides of the equation, so b squared will get cancelled. And we have a squared on both sides of this equation, so a squared also will get cancelled. After we cancel those two expressions, in this side of the equation we have to live with 2ab, and the other side of the equation we have 4x squared minus 2ab. So if we found out that 2ab equals to 4x squared minus 2ab, so here we add 2ab to this equation, and we get that 2ab plus 2ab is 4ab. So 4ab equals to 4x squared. Here we divide this equation by 4 and finally get that x squared equals to ab. X squared equals to ab. Our mission is to find out the area of this circle that is described by trapezoid ABCD. So actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Okay, again, the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total we found out that the area of our circle is equal to pi x squared. But we just right now found out that x squared equals to ab. Therefore we substitute x squared in this equation by ab, and we get that in total the area of the circle equal to pi times x squared, and x squared is ab. So in total, if you found out that the area that we are looking for in this question, that is the area of the circle that is described by trapezoid ABCD, is equal to pi times ab square units. And that is the answer to the question. Repeat again, if you found out that the area of this circle that is described by this trapezoid ABCD is equal to pi times ab square units. So in the next step, I'll summarize the lecture. So in this lecture, I found out the area of this circle that is described by this trapezoid ABCD. We know that this is side AM, that is equal to A units in its length. This is side AB, that is equal to B units in its length. Again, our mission is to find out the area of this circle. We know that the trapezoid is quadrilateral with one pair of parallel sides. So in this trapezoid ABCD, side AD is parallel to side BC. Okay, so first of all, we have here rule 2. According to rule 2, the length of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle, this is the common standpoint point P. For this common standpoint point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, all two are equal to each other. That is to say, PA equals to PB. So here we have the common standpoint point A. From this common standpoint point A, we have two tangents to this circle, tangent AM and tangent AB. And according to all two, they are equal to each other. That is to say, AM equals to AP. But AM equals to A, therefore AP must be also equal to A according to all two. Likewise, this is the common standpoint point B. From this common standpoint point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to all two, they are equal to each other. That is to say, BM equals to BQ. But BM equals to B units in itself, according to what is given as the question. Therefore, BQ must be also equal to B units in itself, according to all two. BQ equals to B units in itself. Okay. In the next step, we define the center of this circle. This point is point O, and we join point O and Q together by straight line. Point O is the center of this circle, point Q is the point on the circle itself, therefore OQ is the radius of this circle. We define the radius of this circle as x, so OQ equals to x, it is the radius of this circle. And because of the fact that the radius OQ is 1 to point Q, that is the point of tendency of tangent BC with this circle, and whenever you have radius that is 1 to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. Likewise, we joined points O and P together by straight line. OP is of course the radius of this angle, that is equal to x, and because of the fact that the radius OP that is equal to x, the radius OP is 1 to point P, that is the point of tendency of tangent AD with this angle, and whenever you have a radius that is 1 to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. In the next step, we did a construction, that is to say, from this point A, we go perpendicular on BC. Again, from point A, we go perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point N. As I already mentioned before, ABCD is a trapezoid, therefore side AD is parallel to side BC. So actually, those two angles are located between the parallel lines AD and BC. Those two angles are defined as one-sided interior angles, and according to Rule 17, the sum of two one-sided interior angles that are located between parallel lines is equal to 180 degrees. So the sum of those two angles must be equal to 180 degrees according to Rule 17. But this angle equals to 90 degrees according to our construction. So 90 degrees plus the size of this missing angle, in total the sum of those two angles must be equal to 180 degrees according to Rule 17. Therefore this missing angle must be equal to 90 degrees in its size. Okay, so in the next step we did another construction. That is to say, from this point O, that is the center of this circle, we go perpendicular on AN. Again, from point O, we go perpendicular on AN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN. This point is point T. By doing this construction, we have the small quadrangle APOT. Inside this quadrangle APOT, we have 1. So inside this quadrangle APOT, we have 1, 2, 3 right angles. So again, this angle equals to 90 degrees according to rule 17. This angle equals to 90 degrees according to our construction, and this angle equals to 90 degrees according to rule 1. So in total, inside the smooth quadrilateral APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle in total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrilateral APOT, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at this rectangle if not a square. So we relate to this quadrilateral APOT, so rectangle because it has 4 right angles. Okay, so anyway, we actually found out that this angle equals to 90 degrees. Okay, so inside quadrilateral TOQN, inside this quadrilateral, we have 1, 2, 3 right angles. This angle equals to 90 degrees according to rule 1. This angle equals to 90 degrees according to our construction. And this angle also equals to 90 degrees according to our construction. So in total, inside quadrilateral OT and Q, we have 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle, in total it must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 pieces angle must be equal to 90 degrees in its size. Okay? So, actually we found out that the big angle POQ, this is angle POQ, is equal in total to 90 degrees plus 90 degrees, that is 180 degrees. And because of the fact that angle POQ is equal to 180 degrees, it means that line segment POQ is a straight line. Any angle that is equal to 180 degrees in size must be a straight line. So POQ is a straight line. If POQ is a straight line, then PQ is also a straight line. Okay, again, because of the fact that the big angle POQ equals to 180 degrees in size, therefore line segment POQ is a straight line. If POQ is a straight line, then PQ is also a straight line. So, in this shape, APQN, we have four sides. Again, in this shape APQN, we have 4 sides. Because of the fact that PQ is a straight line, so in shape APQN, we have 4 sides. AN is a quadrilateral, is a straight line, NQ is the other side, AP is the first side, and PQ is a straight line, therefore it is the 4th side of shape APQN. So in total, in shape APQN, we have 4 sides, and therefore shape APQN is a quadrilateral. Okay? So again, shape ANQP is a quadrilateral because it has 4 sides. So in quadrilateral APQN, we have 4 right angles. Again, in this quadrilateral APQN, we have 4 right angles. Okay, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle, if not a square. So we relate to this quadrilateral APQN is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle APQN, side AP must be equal to the opposite side NQ, but AP is A, therefore NQ must be also equal to A units in its length. Likewise, according to the third rule, in the third rectangle APQN, side PQ must be equal to the opposite side AN. But PQ equals to x plus x, that is 2x, it is actually the diameter of this circle, and therefore AN, the opposite side AN, must be also equal to 2x units in its length. What is the length of this missing 9797 Bn? From the moment it is very easy to see that Bn in total equals to Bq minus Nq. Again, Bq minus Nq equals to Bn. Bn equals to Bq minus Nq. So Bn in total equals to Bq. Bq is B. Bq is B. According to what to? Minus Nq. Nq is A. So in total, Bn equals to B minus A. Bn equals to B minus A. What is the length of side AB? Side AB in total equals to A plus B. Again, AB in total equals to AM plus MB. That is to say, AB in total equals to AM, that is A, plus MB, that is B. So in total, AB equals to A plus B. So in the next step, I copied the right triangle A and B in a new equation, implemented the Pythagoras theorem on this right triangle A and B. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle A and B that I copied from the original drawing. So as I mentioned before, the hypotenuse AB is B plus A, AN equals to 2x, and BN equals to B minus A. So according to the Pythagoras theorem, on this right triangle ABN, AB squared, that is the square of the hypotenuse, equals to AN squared plus BN squared. Again, AB squared equals to AN squared plus BN squared. AB is B plus A, therefore B squared is B plus A squared, and is equal to AN squared. AN is 4x, therefore AN squared is 4x squared plus Bn squared. Bn is B minus A, therefore Bn squared is B minus A squared. So in total, if we found out that B plus A squared equals to 4x squared plus B minus A squared. We open the brackets on both sides of this equation, and we found out that B plus A squared equals to B squared plus A squared plus 2 times AB, and it is equal to 4x squared plus B minus A squared. B minus A squared equals to B squared plus A squared minus 2 times A times B. Here we have B squared on both sides of this equation, so B squared will get cancelled. We have also A squared on both sides of this equation, so A squared also will get cancelled. After we cancel those two expressions, in this side of the equation we left only with 2AB, in the other side of the equation we left with 4x squared minus 2AB. So in total we found out that 2AB equals to 4x squared minus 2AB. Here we added 2AB to this equation, and we found out that 2AB plus 2AB is 4AB, so 4AB equals to 4x squared. Here we divided this equation by 4, and finally found out that x squared equals to AB. X squared equals to AB. Our mission is to find out the area of this circle that is inscribed by this trapezoid ABCD. So actually you know that the area of any circle is equal to pi times the radius of the circle squared. Again, the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total, we found out that the area that we are looking for, that is the area of this circle, is equal to pi x squared. But we have already found out that x squared equals to AB. So we can substitute x squared here by AB. And we did it, and we found out that the area of the circle equals to pi times x squared, and x squared is AB. So in total, the area of the circle equals to pi times AB. Repeat again. And we found out that the area of this circle is equal to pi times AB square roots. Okay, thank you very much.